Okay, so we're back with round two of thermodynamics. This time we're talking about specific heat. There's two things you got to keep in mind here. There's two very similar things. There's something called heat capacity, and there's something called specific heat capacity. Let's talk about heat capacity first. Heat capacity is talking about how much energy to raise temperature by 1 degree Celsius or Kelvin, because it doesn't matter, right? So a heat capacity is for something bigger, like if you have a block of wood and you want to know how much to heat it up, when you heat it up, how much energy it takes, and it will go up by a certain amount of degrees. All right, so it's how those tie together. All right, there's a formula for this, but let's jump to specific heat capacity first. It's similar, but it's got a different flavor to it. It's how much energy to raise 1 gram 1 degree Celsius. All right. So specific heat capacity is going to be by material. Okay. Heat capacity by itself is just going to be by object. All right. So heat capacity, the formula for it would look like this. Q is equal to C delta T. All right. So the pieces here, Q is the heat. Heat is going to be in joules. Delta T is going to be the change in temperature, and that's going to be in Celsius or Kelvin. And C is your heat capacity. All right, so this is going to be in joules per Kelvin, or joules per Celsius, or it could even be in kilojoules. You have to watch out for that, but it works the same way. So what this is saying is it's measuring if this goes up. So if we're heating something up by 10 degrees, that's going to increase the amount of heat that's inside of there. But they're not going to increase at the same rate. Okay, so this is your rate. If I get this block of wood 10 degrees warmer, it'll have maybe 100 more joules. But if I have this block of metal 10 degrees warmer, it will get less than 100 joules of extra heat. All right? So it's for a whole object. Now, where you get more concrete is with the specific heat. All right? So this is per gram. So the formula is slightly different. So this formula is going to be Q is equal to mc delta T. Now what's different here is this is still heat. It's still in joules. This is still your delta T, or still your change in temps. It's still going to be in grams or Kelvin, or Celsius or Kelvin. Here's your mass. This one has a mass that's separate. This can be in grams or kilograms. It depends on the constant here. And this guy right here is your specific heat capacity. Specific heat capacity. All right, so this will depend on the material. So water has a heat capacity, or specific heat capacity. Ice has a specific heat capacity. All of these materials have their own. We'll talk about those in a second. So your specific heat capacity is going to be joules per gram Kelvin. All right. Now it could be slightly different units, but they're all going to be the same type of format here. So the difference is this is one material, and this is just anything. So your heat capacity could be for a box, it could be for any miscellaneous thing, but if you want to get to the nitty-gritty, then you need the specific heat capacity. You're going to use specific heat capacity much more often, but you should at least be aware that you can do this with a random object, and that's just heat capacity, no specific about it. So here we're going to talk about the most important specific heat capacities. You don't have to memorize these, but these are the ones that show up 99% of the time. Just mostly it's water and then various metals where you have one to represent that. So remember your equation is going to be Q is equal to mc delta T. So this C has a unit of joules per gram Kelvin. Okay, so water has a value of 4.18. All right, so that's the value for water, but sometimes you'll see it written in a different way. You might see it written as 4180, but what they're doing is they're not showing you joules per gram Kelvin, they're showing you joules per kilogram Kelvin. All right, this one is more of a chemistry point of view, whereas this one is more of a physics point of view. We are going to go between them because we don't really care either way, but because this is using kilograms like physics, this is using grams like chemistry. There is another way they could represent it, so they could say 4.18, but they're doing kilojoules per kilogram Kelvin. So you just need to be aware and watch out those units. You should be able to use any one of these. It's not too difficult to switch them up. All right, ice has a value of 2.03, and these are going to be in joules gram Kelvin. Water vapor has 2.08. That's going to be in joules per gram Kelvin. And then to give you some comparison, iron is going to be 0.45 joules per gram Kelvin. Now you should notice something here. You should notice that iron is very small. And all the metals are going to be very small. This means that it does not take a lot of energy to heat it up. All right? By comparison, water is very big. Water has a relatively large specific heat. This isn't just for the ones that we picked here, but in general, water has a big specific heat. This means that it takes a lot of energy to get it hot. You've seen this before when you're boiling water to make noodles or something like that. It takes a long time for the water to get hot, to get to its 100 degrees. The reason is because it takes a lot of energy every step of the way. If you put an empty pan on there, the pan will get very hot very quickly because the empty pan has a very small specific heat. So here's the types of problems you'll see. We're going to do one with just heat capacity in general, and then we'll do some for specific heat. So in this one, a brick is given that many kilojoules of energy and heats from 15 to 25 degrees Celsius. What is the heat capacity? So the heat capacity formula is Q is equal to big C delta T, right? It took in 120 kilojoules. We'll just leave it in kilojoules, how about? And that's going to equal the specific heat times the change in temperature. 15 to 25 means you went up by 10 degrees, so divide by 10. So that means that 12 is equal to the specific heat. Now this is going to be kilojoules per Kelvin, or Celsius, doesn't matter either way. You could change it to 12,000 joules per Kelvin. This means that it takes 12 kilojoules for every degree you want to warm up this brick. We didn't say how much mass it has. We don't care about a per mass ratio here. We just know that that's how much energy it takes to warm it up. Let's look at a specific heat version now. So this one, the temperature of 335 grams of water changed from here to there. how much heat did the sample absorb. So we're going to use our specific heat formula. So we've got Q is equal to mc delta T. Q is going to equal the amount of heat, which we're looking for. M is the amount of water, 335. We'll just use the grams because that's the number we have for C, right? It uses grams. Times C is 4.18 times the change in temperature. There to there, we went up by 1.9. Alrighty, so we multiply all those together, we're going to get 2,661 joules. Now we should round that off to 3 sig figs, it looks like 266 joules or 2.66 kilojoules. Any way you want to represent that. Okay, let's look at the next one. How much heat in kilojoules has to be removed from 225 grams of water to lower its temperature? Well, do you think you can do it? We'll give you a head start. Pause if you want to try it. We're going to start with the same formula. Q is equal to mc delta T. Q is what we're looking for here. M is going to be 225 times C. It's just water, so it's never going to change. 4.18. So times delta T. Delta T is going to be, we're dropping by 15 degrees. Okay, now for me, I don't like to worry about the positive or the negative for this value here. I like to think about my answer and then use that. So we're going to get 14.1 kilojoules from here, 14,100 about. Now this much energy is lost from the water, okay? So it's how much energy has to be removed. This much energy has to be removed. All right, so just however you need to specify it. Usually they kind of are interested more in the magnitude, just the number, but there are situations where you have to specify if the energy goes in or out. You can worry about the signs if you like to keep track of that. I just like to think about it here. The temperature's going down, you're going to lose energy and not gain energy. Here's another one. If you want, pause it out so you can try it. Okay, so we have Q is equal to mc delta T. So this time we know how much joules got in there. It's going to be 1080. We know the mass is 140 times C. We're looking for the specific heat, so it's just going to be times C. If we're going from 98 to 62, that's a change of 36.2 degrees. So doing some math here, we're going to get C is equal to 0.27. This is going to be in joules per gram Kelvin. Does this make sense? Yeah, that's a reasonable answer. It's a metal, so it's going to be a small number. It's going to be somewhere in that range there. All right, I think we have one more here. A piece of iron is 200 grams. Given that much heat from room temperature, what's the final temperature? So if you think you can do it, give it a try. Pause the video. I'm going to catch up to you now. So Q is equal to mc delta T. So I know the energy is 540 is equal to 200 grams times 0.46. For this one, we have to solve for delta T as a whole here. You could split it apart if you wanted to, plug in a difference into there. I don't think it's worth it. I'm going to solve for delta T first. Delta T is going to equal 5.9. Now, this isn't our answer here. This is how much the temperature changed. Now, because I don't worry about positive or negative, I'm thinking about, it was given this much energy. So the temperature is going to go up. Since the temperature goes up, it went up by this much. So the temperature started at 18, and then we added 5.9 to there. So that means the final temperature is going to be 23.9 degrees Celsius. You could switch it to Kelvin if you want. But unless it asks for something specific, either unit is okay. Just don't use Fahrenheit. Okay, that's it for today. There's a practice. Have fun with it. Like and subscribe.